All right, part 2. Okay, so let me see where we want to try to get to. I would say let's try to get to not starting to do any equilibrium stuff with acids. So the second half, so we'll do up to this point today, I think, because it really is not bad. So the second half is doing equilibrium on acids. The thing that's super nice about it is that they're only ever coefficients of 1. So you never end up with any complicated algebra at the end. So after 16, 17 feels easy. Okay, so first thing, kind of review of acid-base definitions. The best thing you want to think when you're trying to keep this all straight in your head is that acids donate protons, or H+. So hydrogen is 1 proton and an electron, no neutrons. So if you have the electron gets lost, all you're left with is a proton. So that's why we call H+ a proton frequently. But when you end up putting H+ into water, it bonds with a water molecule and makes H3O+. So almost always you will see me write this type of reaction as HCl plus water forms H3O plus Cl minus. Okay? Both of those, this one that's written up here and the one I wrote, are completely the same thing. They're both acceptable. It's just that you're assuming the water in the first one, and I'm explicitly writing the water in the second one. Okay?
You said acids were what?
Proton donors, or H+ donors. So meaning, in the one we've shown here, HCl is acting as an acid because on the product side, it's turning into Cl- because it gave up its H+. Okay, so acids are always going to have hydrogen on them. And when they lose that H+, you should see a hydrogen missing, but you should also go down in a charge unit. So it's neutral on the reactant side, it's negative on the product side, because it hasn't just lost the hydrogen, it kept the hydrogen's electron with it. So when something acts as an acid, the thing it turns into on the product side is 1 less hydrogen and 1 less charge unit. So these are all like different ways of saying the same thing. But the key point is you see it turn into the same molecule minus that H+, removing that H+. So that's what defines an acid. Some people will say it a slightly different way. They'll say it forms H3O+ in solution. Well, that's the same thing. If it gives up its H+, it's forming H3O+. So either you're talking about the molecule itself or the consequences of what the molecule does. All right, a base, there's kind of 2 different types. Let's actually talk about the second one that's listed first. So in this example, NH3 is a base, and they're the opposite of an acid in that they accept protons. So the acid gives away the proton and the base takes it. So you can see NH3 turns into NH4+. It took an H+ from somewhere. We'll get to where it got it from in a second, but. And this is why I like writing the acids as reacting directly with water, because if you don't, it gets confusing when you get to the bases. So let me actually just show you, the acid example we gave earlier was HCl. Let me show you what happens when HCl and NH3 react together. And then I'll show you kind of how water can take the place of either an acid or a base. Okay, so an acid has to give up its H+. So HCl, this H here, is going to be given to that NH3. It's an acid, it gives up the H. NH3 is a base, it takes the H. Okay, those are the two key points you always remember. Acids giving up that H+, base is taking that H+. So the things they turn into, the acid should be one less hydrogen, one less charge unit. So we'll see lots of examples of different acids and show what do they turn into. That has a name. It's called the conjugate base. It's a J first. It's a joke in our house how bad I'm at spelling. Conjugate base is the thing the acid turns into. And then the base turns into one more hydrogen and one more charge unit. Okay, and that's called the conjugate acid. So this is if we actually mix an acid and a base together, things we know of as an acid and a base. But lots of times we just stick an acid in water or we stick a base in water. And the thing is, there is still, you always have to have one with the other. You can't have an acid without a base. So when you put them in water by themselves, the water is the thing that acts as the opposite thing. So if we go back up to the HCl, remember HCl was an acid, so this hydrogen is actually given to the water. And that's why it turns into H3O+. So the water in this instance is acting as the base. It's the thing accepting the H+. But then when we go to the base, we always need one and the other. So the base is is taking a hydrogen, and the place it gets it from is from the water. So now the water is acting as an acid, it's giving up an H+, and the NH3 is accepting it. So this property of water is called amphiprotic or amphoteric. It just means it can act as an acid or a base, depending on what it's in the presence of. So when we look at these, the pairs are the NH3 and the NH4, and then the water and the OH minus. So water, one less hydrogen, one less charge unit. NH3, one more hydrogen, one more charge unit. And maybe that's like a good way to think of the base and the acid too, is what does it turn into? How does it change? So we said earlier with the acids, another way people describe it is that in water, it makes H3O+. The way we describe bases is in water, it makes OH minus. The OH minus is called hydroxide. And the H3O+ is called hydronium. Usually you call them ions, hydronium ion, hydroxide ion. Okay, so that's one kind of base. We'll explain why it's called a weak base in a second, but those are weak bases. Strong bases, again, we'll get to that in a second, are actually the salts that dissolve of hydroxide. So all of the first column, and to some degree, calcium, strontium, and barium that are in the second column. They are sort of considered, when you put them with the hydroxide ion, they are sort of considered a strong base. So the reason why they're okay to be a base, even though they don't technically accept a hydrogen, an H+, is because they make OH- when you put them in water. They just dissolve and make the OH-. So if you did calcium hydroxide, remember calcium's a 2+ ion, and so it'll actually have 2 hydroxides associated with it. So it'll make 2 hydroxides for every 1 mole of calcium hydroxide that you put in there. So that would also be this kind of type 1 base. So it's an ionic compound where the OH- is the anion. They dissolve, and that's why you get OH- as a product. Okay, I know it's kind of confusing when we just talk about it, so let's do some examples. Okay, so on this one, I want you to write me an equation, each one of them reacting with water, and tell me what the products are, knowing that each one of these is an acid. Now, technically, all the other ones are aqueous other than the water. I'm lazy and haven't been writing those. So. All right, so there's the first one, just to give you an example. I'll let you guys finish up the other two. So loses a hydrogen, loses a charge unit. Gains a hydrogen, gains a charge unit. If you're talking about the acid
Yeah, I
and
know
the
I'm
base.
doing it wrong, 'cause
Okay.
I always mess up those charge numbers, even though it's just, you know. So, isn't it supposed to be NO3 plus and H3O minus?
No. So the hydrogen is leaving behind its electron.
Uh-huh.
So it's like you've got the hydrogen here and the NO3, and this is staying with the NO3, and just the proton is going with that guy.
Okay.
So you have one additional electron with the NO3 than you should have, like to balance out the protons in the nitrogen and the oxygen. And then you have one extra proton with the water. So the protons are positively charged, electrons are negatively charged. So that's why.
So then it's not the opposite of what I think it should be, like it used to be.
I'm not sure how to answer that because I don't know what you think it should be. But
I thought like if you lost an electron, that
It's
it
n-
was positive.
it is.
Okay.
So
That's- you're not losing the
you're not
electron.
losing the electron, it's just staying behind with the NO3.
Okay.
Yeah. All right, let me finish off these last two. Oh, there's a carbon missing in there. That should be COOH, COO minus. This is acetic acid. So they all should look extremely similar.
So you're only moving over one hydrogen.
Yes. Now, technically, the one on the bottom is what's called a triprotic acid. So it actually can lose additional hydrogens, but we would always write that as a separate equation. So in reality, you could have 3 separate equations for this. This is phosphoric acid. The first one is technically phosphoric acid. The others would have another name.
So anytime, just for clarification, anytime it's losing the hydrogen, it's going to be minus.
Yes. Well, it's going to be one less because, like, if it starts as positive. So NH4 plus is an acid. So if it reacted with water, you'd still get the well, let me put that in the right order. It's not right or wrong. It's just what I've been doing. So this would be one less charge unit. It was positive and now it's neutral.
Oh, okay. Because it's already plus. So you're
Yes.
just taking that plus
Yeah.
away.
Yeah. And then really, these are examples where it's negative and it's getting more negative.
Okay.
So it's
then
just going
anytime
down.
okay, so the CH3COH is already at its neutral point. That's why it
Mhm.
goes to negative.
Yeah.
So that if it was already at negative, it would be 2 minus.
Yes.
Okay.
Yeah.
Gotcha.
And for this phosphoric acid, I only expected you guys to write that first equation, but I just want you to know that there are compounds with additional, what we call acidic hydrogens, ones that can come off. Now, you'll notice that in this one, we separated those 3 hydrogens in the formula from the other one. And that's on purpose. It's trying to communicate that this one is acidic. It can leave the molecule. Those 3 are not going to leave the molecule. This looks like this. This is a good organic chemistry application. So that molecule, that hydrogen on the end, if it leaves, those oxygens can stabilize that negative charge really well, that electron that's left behind. This hydrogen, if it was to try to leave, that negative charge, carbon would not stabilize that very well. It's called a carbanion, and it's super reactive. It would just immediately react with something else, probably just a neighboring hydrogen. So those ones will not come off. There's no way for you to really tell for sure. You can kind of infer it from the fact that they're written separately from the other hydrogens. But, you know, I'll tell you like how many are going to come off or how many are acidic. I'm sure I can think of an example where they write them together even though they don't all come off. Okay, let's do these ones to show it as a base. And the first two are type 1 and the second one, or I'm going to change this because that's the exact same one we did before. In fact, we did this one too. Well, no, we should do those in the notes because it's good to have that later. Okay, let's do, maybe I'll give you 2 more for these actually. Okay. There's a good example. Okay.
Is it like the same as the acids, or just breaking down the hydrogen into the?
Well, it's the reverse of the acids. So the hydrogen you're gonna gain an H plus for the bases. For the bottom 2. The top 2 are different. So maybe we can do one of each together in case you guys are stuck. So when it has OH in the formula, that's gonna be one of these type 1s where you don't have to write the water, you just have to show it breaking up into its ions. Oh, that should be a minus. Okay. So you're forming OH minus. That's kind of the key similarity between type 1 and type 2. You feel like you're missing, I changed those at the bottom.
No, I'm just looking at the first one. I don't know why, I wrote it like that. I don't know why I wrote it like that.
Yeah, that's not right. It's okay. It's because you were thinking of it as those type 2 ones. So anytime you see, so remember, if you remember back to polyatomic ions, OH minus is hydroxide ion. So anytime you see a formula with OH minus in it, you can assume that it's a type 1. I think I have a list of these. Do I? I have the list on the exam equation sheet. But like I said, it's all of the 1A, so LiOH, NaOH, KOH, RbOH. You're not going to see those ones. And then these 3 to some small degree. So CaOH2, SrOH2, and BaOH2. And those are the only ones you're going to see that are this type 1 type.
So then you don't add the H2O. It's just
No.
kind of
It's assumed that it's in there because you say that these are aqueous. That's what aqueous means, is dissolved in water, but you don't add it. If you were to add it, it would be water on one side and water on the other. Like it isn't directly involved in the reaction.
So then it's just a matter of that OH being taken out. Or,
Yes,
I mean,
being
just
dissolving
separated.
and then being in the water. Because like with the type 2 bases, we form the OH minus from a water molecule. So we still are making OH minus. That's the similarity there. But it's formed from water in type 2, whereas in type 1, it's just because the thing dissolves. So for the first one, for type 2, HS minus, again, a base is going to accept a hydrogen, so it should go up in a hydrogen, up in a charge unit. So it should be H2S. Neutral, because you went from negative up to 0. And then the other product is that OH minus. So like if it's reacting with water, it's going to be super easy to identify a base because one of the products is going to be OH minus. If it's reacting with water, it's going to be super easy to identify the acid because it'll be H3O plus. Where it'll get more confusing is it an acid and a base together without water really involved? Because in that instance, they neutralize each other and you don't see the OH minus or the H3O plus at the end. So we did an example of that up here really early on. So you can see like you don't even see OH minus and H3O plus because the hydrogen didn't get transferred to water, it got transferred over to the NH3. So if it's reacting with water, it'll be easy to identify. If it's reacting with another base, you're gonna have to look at how does it change? Does it go down in hydrogens, down in charge unit, or up in hydrogens and up in charge unit? Okay, one more minute to do those last two and then I'll write them up as well.
So then anytime that you see the OH, that's when you're not directly adding the H2O.
In the formula, yeah, when you see the OH in the formula. Yeah, that's right.
These last two, you would add the H2O.
Mhm.
And then is it still a base?
It is because it makes OH minus.
Okay.
Or another way of saying it is because, no, let's just say it makes OH minus. Because the top one's going to be different. So.
I think the charge of this one is confusing me.
Yeah, I mean, that may just take like seeing more examples, but like I said, you guys should really plan to start the chapter 17 homework because next weekend you'll have the practice exams too. Not next weekend, but the next weekend. So do as much as you can on 17 over the weekend. Ideally, you've done some of 16 already too, so it should be okay. And like I said, don't worry about the states that I'm listing here because, you know, it's a multiple choice exam. You're not going to be writing these out.
Did you write that as C5H6?
You could, anytime you're adding a hydrogen to a base though, I would write it separately. I would separate it because that's an indicator that,
It's a base.
yeah, that hydrogen,
Was added.
yeah. I'm going to say it a slightly different way in a minute, but. Okay, so there's your last two. One of the notes on the calcium hydroxide is make sure, because the calcium was a 2+, there was a 2 there. So in the balanced equation, you need to be making 2 OH minuses. That's the only time you're going to see a coefficient in an acid-base reaction. Like a coefficient other than 1. Okay, so we talked about this naming of conjugate base and conjugate acid. So whatever the acid turns into is called the conjugate base. That may seem confusing. In a second, I'll explain why. Whatever the base turns into is called the conjugate acid. The reason why we call this thing the conjugate base is because if the reaction went the reverse direction, which can happen because we know equilibrium exists, if the reaction goes the reverse direction, that thing will be acting as a base. If we define a base as gaining an H+, look at how it looks when it turns back into H2SO4. It gained an H+ in that direction. So in this direction, it's losing an H+, and in that direction, it's gaining an H+. So the reactant, we call that an acid. The product that could turn back into the reactant, we call that a base, because in the reverse direction, it acts as a base. And you can kind of show this by like looking at what H2SO4 could do in water, acting as a base. So a base, we know it's going to be OH minus, and then it's gaining a hydrogen and gaining a charge unit. So it turns back into H2SO4 if it acts as a base. So every time you have an acid, the thing it turns into has the ability to act as a base. And the opposite's going to be true too. Anytime you have a base, the thing it turns into has the ability to act as an acid. So let's look at one of those. So NH3 turns into NH4. Just kind of proving the point here. If you had NH4 in water, it would produce OH minus. Oh, sorry. It would produce H3O plus because it's acting as an acid, we said, and NH3. So it is acting as an acid over here. If it were to go the opposite way, it would be acting as an acid. So here it donates the H+, and here it accepts the H+. So it really is just the direction you're talking about that defines what the thing is doing and therefore what you call it. So it'll ask you questions about like select the correct acid-base pairs. So, water and something, NH3, that's not an acid-base pair. They should look almost identical, only differing by an H+. And whichever one has more hydrogens, that's the thing that could potentially be an acid. They won't make you necessarily say which one is conjugate versus which one is just acid or base. They'll just have label the correct acid-base conjugate pairs. So they're looking for things that look identical other than the fact that they differ by an H plus. The one with more hydrogens is the acid. The one with less and less charge is the base. This stuff, I'm going to briefly say it, but we're going to come back to it on next week. So there's a list of 6 strong acids in your exam equation sheet. I'm trying to see if it's listed in here as well. I don't see it immediately. But they're listed in your exam equation. Oh, they're right there at the bottom of that slide. These are the only 6 that we're really going to be familiar with that act as a strong acid. And all that means is that it's completely product favored. So it goes completely to products. We'll note this by only drawing the arrow in that direction. So another way of saying that is the equilibrium constant is really, really big. K is big. Much bigger than 1. So there's going to be hardly any reactants left over. Not enough to even think about. And then a weak acid, which is everything else other than those 6, is going to have some equilibrium balance point. Okay? So we'll draw a double arrow there to represent that it is kind of balancing between both sides. The K is going to be small-ish, so it'll be less than 1, but just like all the other Ks that we've done in chapter 16, it could be 10 to the negative 3rd or 10 to the negative 7th or 10 to the negative 10th, right? There's a big range there in how small it could be. And that just defines that balance point. The reason why this is so important is because one of the products, the H3O+, that's the thing that causes all of the properties of an acid, like acids are corrosive, acids taste sour, like all of these things are caused by the H3O+. So like if I have 1 mole of a strong acid, that will make 1 mole of H3O+. But if I have 1 mole of a weak acid, that might only make like 0.1 moles of H3O+, or 0.001 moles of H3O+. So you're getting a lot less of the acid properties with a weak acid, even if they're the same concentration as a strong acid. Okay? And we'll calculate the details of that next week, which is going to be this. So we'll get there next week. Okay, so I want to do some of the basic calculations, not the K expressions. Yeah, here. So go to where it says KW. So this is going to be all of the pH, H3O plus concentration, pH concentration. We're going to throw in this idea of pOH, okay? So this all depends on the fact that in a water solution, this reaction is always happening to a very, very small extent. Water reacts with itself and forms H3O plus and OH minus. Okay, it happens a very, very small amount. The amount being the K is 1 times 10 to the negative 14th. Okay, so a very small amount of the products are being made. But the thing that's nice, remember we don't include liquids in the K expression. So it's just those 2 products. So if we know one of these, we can then determine the other one, because the product of them will always be 1 times 10 to the negative 14th. Usually, we're almost always going to care about the H3O+. We're going to define solutions in terms of H3O+ and pH. So if you're doing something that has a base and you solve for the OH minus, you're probably going to have to utilize this to get the H3O plus. So that's on your exam equation sheet, I think, that, you know, equation, if you want to think of it that way. Let's come back to these after I summarize everything. Okay, and then the other big concept here is pH, and tied to that is pOH. So don't let the P scare you. All it means is take the negative log. So logs, I don't care if you don't understand what it is, just know how to do it. So let's clear this out. So on this calculator, it's right here. Okay. So let's say that I have an H3O plus concentration of 1 times 10 to the negative third. Okay. 1 times 10 to the negative third. And I take the, sorry, P means negative log, not just log. Did I write that there? Yep, negative log. P means take the negative log. So there are pHs, pOHs, pKa's, pKw. These just means take the negative log. So pH is take the negative log of the H plus. pOH, take the negative log of the OH minus. pKa would be take the negative log of the Ka. All it does is take numbers that are much less than 1 and puts them in a more usable form. So if your number is just 1 times 10 to the some exponent, taking the negative log of it will make it equal to that number. So if it's like 1 times 10 to the negative 14th, you take the negative log, will be 14. If it's 1 times 10 to the negative 4th, the negative log will be 4. Now often these will be different numbers, right? So like 2.5 times 10 to the negative third. I know, what's the exponent though? Give that to me in... Oh, no, that's right, okay. So 2.5 times 10 to the negative third, the negative log of that is 2.6. This doesn't always come out to be that pretty. Let's see, 1.7? Okay, 1.7 times 10 to the negative third is equal to 2.7, almost 2.8. So these will actually be inverse. The smaller the number gets, meaning a big negative exponent, smaller the number gets, negative exponent, the bigger the number of your answer will be. Okay, what do we use this for? Acids and bases are used so much in everyday discussions. Like, I've told you guys I'm obsessed with gardening this summer. So like soil pH is a big deal. So even some random person who gardens, who's never done chemistry before, needs to have a general understanding of pH, or at least how to interpret it. So they might know that, you know, blueberries should be in a pH of like 3 to 5 at the most. Okay? That is a measure of how acidic the soil should be. So everything with a pH under 7 is considered acidic. Ignore the pOH for now. And everything above 7 is considered basic. And what that pH is the negative log of the H3O plus. Okay, so the more H3O plus you have, the lower the pH is going to be. So on this scale, this has more H3O plus. That's why it is more acidic. And over here, it has less H3O plus, making it more basic. So they're inverted in the sense that as the H3O plus goes up, the pH goes down, and vice versa as well. The other thing to remember is that this is all tied to the OH minus, right? We said H3O plus times OH minus is 1 times 10 to the negative 14th. So if this goes up, that has to go down. So what that means is, and I'm going to write this out up here, is that higher H3O pluses will correspond to lower pHs, but that also means that the OH minus is lower. So any solution that has a pH less than 7 is acidic, which basically just means that it has more H3O plus than OH minus. It has a high H3O plus amount and a relatively low OH minus amount. Okay, so we've summarized 2 of these calculations, I think. So this little chart is me, it's not in your book. This is how to get between all of the different ways we express acid-base numbers. So the ones we just talked about are pH and H3O plus. So to get from, that's this arrow, to get from pH to H3O plus, that formatting is stupid. It got messed up. pH equals the negative log of the H3O plus. Okay, so if you have the H3O plus, I did that wrong direction. That's if you have the H3O plus and you want to get to the pH. You plug that in here. Now, logs don't work, like you can't divide by a negative log to undo it. The way you undo a log is like this. So if you have the pH and want to know the H3O plus, so this direction, you do 10 raised to the negative pH. And that will give you the H3O plus concentration, which should make sense. Because like we said, we did 1 times 10 to the negative third, right? And that told us the pH was 3. So vice versa, if we want to know what the H3O plus is, 10 to the negative 3, that gives us the H3O plus. I think logs started before calculators. My dad's old enough that he used a slide rule when he was in engineering school. And logs are kind of a carryover from that. It just made it easier to work with numbers because then they weren't these ridiculous 0.0000, you know, scientific notation. They didn't have to use that as frequently. Okay, the other one we talked about is this, going between H3O plus and OH minus. So that's not hard. You just take 1 times 10 to the negative 14th and divide by one of them, the OH minus. That'll give you the H3O plus. And vice versa. If you have the H3O plus, 1 times 10 to the negative 14th, divided by that, it'll give you the OH minus. All right, let's do a couple of those example problems. I wish there was one that was a better mix. Oh, these ones are. So let's skip over some of these that are like just one type of problem. And we're gonna do some of these mixed ones. So let's do the first one. And
Close warm.
the only one we can do is the first one. Maybe that's why I left all those simpler ones. Okay, I take it back. Let's do the last 2 on this page. So determine for the H3O plus, determine what the OH minus is. And for this OH minus, determine what the H3O plus is. It is just above the weird calculation arrow thing. So you're using the equation that's at the top of that next page. That's not right. Oh, yes, it is. Okay. Okay, so anything above 10 to the negative 7th, like higher than 10 to the negative 7th, is going to be considered a higher H3O plus concentration or OH minus, because the two of them together, when you multiply them, have to be equal to 10 to the negative 14th. So in a neutral solution, both of them would be equal to 1 times 10 to the negative 7. So no acids or bases, they would both be equal to 10 to the negative 7th. So if you go higher, meaning a smaller negative exponent, like 10 to the negative 3rd, then that means it is more acidic. And then you can see from this that the OH minus the OH minus is smaller than the 10 to the negative 7th. So the H3O plus goes up and the OH minus goes down. And the middle point is the 10 to the negative 7th. So when I say it goes up from there or down from there. And then similarly, if the OH minus is higher, 10 to the negative 3rd, the H3O plus has got to be lower. The thing that's going to get confusing is the fact that it's a negative exponent. So higher means, I mean, I guess we've been dealing with this with K's the whole time. So a smaller number is a higher negative exponent, like 10 to the negative 12th. Okay, why don't you give me the pHs of each of these solutions now? Oh, just kidding. Go to the next page. Go past that calculation page, and let's do these ones. So just do the pH column, and we're gonna do all 4 of those.
Is pH the one with the log?
Yeah. So the equation you're using is negative log of the H3O plus gives you the pH. And for the bottom ones, you're gonna have to also use the fact that OH minus times H3O plus is equal to 1 times 10 to the negative 14th. I gotta stand up again. Only 2 other types of calculations to do, and then we'll be done. They're on the same page, though.
It's nice when everything comes together.
Oh, good. After 3 hours in here, it's almost like my brain feels dizzy. I get that feeling though when I teach 3 classes in the same day because it's all the same material. It's like over again. I'm like, oh. The more I can find to talk less and make you guys do practice problems, the better. 'Cause then I don't feel like I'm repeating myself. Okay, so we're good with these. One little additional cheat that makes some of these easier is if I were to take the negative log of this whole equation, I would end up getting, I'm going to invert these a little bit, but pH for negative log of the H3O plus POH, which we're going to talk about in a second, it's just the negative log of the OH minus, would be equal to 14. So when I did like this calculation, for instance, I did not use the OH times H3O plus equals 1 times 10 to the negative 14th. I actually just took the negative log of OH minus, which gave me the POH, and then I subtracted that from 14. So the negative log of this is 8, and 14 minus 8 is 6. So that's one like different way that you can get from OH minus to pH. So this is where the arrows come in. You can either go OH minus to H3O plus to pH, or you can go OH minus to POH to pH. That's what this equation lets you do. Okay, so it's just 2 different directions to get from one to the other. Okay, so the last thing, we talked about this one. Now the last thing is OH minus and POH. It's identical to H3O plus. It's just OH minus. So negative log of the OH gives you POH, and 10 to the negative POH will give you the OH minus. And the POH scale is exactly opposite of the pH scale. You'll never hear people in everyday conversation talking about POH. We always talk about things in terms of pH. And to be honest, I'm not sure why we bother with it then, but simply because it's a thing, just like pH is a thing. And maybe because it makes some calculations easier. I don't know why, but we do. So an acidic solution will have a low pH and a high POH. A basic solution will have a high pH and a low POH. Okay, so they're inverse of each other all the time. The H3O plus and the OH are inverse of each other. The pH and the POH are inverse of each other. So let's do the last column. So maybe do the last 2 first, because they're easiest. So to go from OH to POH, we just have to take the negative log. And then from H3O plus, you'll have to take 2 steps. You get to decide, maybe do one way and one the other. You can go through pH first, or you can go through OH and then POH.
does all equal 14.
Mm-hmm.
I guess I gotta save myself a lot more time.
I'm glad you did it because I was like, do it the long way. I hope. Was this 141 or 142?
41.
Okay. Just looking at where my classes were next semester. Morning tour and Hale, and the other one's in 142. And they're all full almost. There's a few seats in the other two, but
You're the only one teaching chem in the fall
the lecture.
lecture.
I don't do labs. I don't like labs.
How is your guys' lab going?
It's fine. I mean,
Did he talk about the lab reports?
like, yeah, we have. So we don't have lab today, but then we have 2 due next week. So
It's nice of them to cancel it.
I think
It's only
we-
once a week, you know.
I think we'll probably have like 1 more after that. Then if there's a total of 3. So it's honestly been fine. Like half the time I have no idea what we're doing, but like he seems satisfied.
He
with
knows
what
what's
we
going
do,
on,
so-
but you don't.
Yeah.
We're just there.
He doesn't
I
seem
think-
like he cares, so I don't care.
Yeah. I mean, I'm sure he cares to some degree, but also you just get to
Well,
the
we
point
all
where you're
show
like,
up and try.
Yeah.
And like what you said
Yeah.
and like what I've heard is like if you're there, you'll get an A.
Yeah.
So.
well, that's better than my class.
Yeah.
So, okay. So you'll have lots of these. The only ones we didn't practice a ton are the reverses. So if you're given pH or POH, I don't even know if I have any of those on here for some reason. Oh no, they're right there. So like if you're given POH, you need to get OH minus 10 to the negative 4.6. Same thing for pH to pH to H3O plus, 10 to the negative 13.2. Like solve that out. Don't list it as 10 to the negative because you're not supposed to leave. That's not scientific notation. That is an operation you need to complete. And if you had one like this where you got to do 2 steps, I would first get the POH and then go to the OH minus. Okay? All right, maybe we'll do this one as like a refresh when we come back next Wednesday, and then we'll finish off all of the material.